Okay, correct. Okay, so the question is, let me just. So the question was, suppose in the previous class, we looked at the following hypothesis or set of hypothesis classes HM, which consisted of polynomial classifiers of degree at most n, right? So for this, I said that as m increases, the estimation error increases, but the approximation error decreases. So firstly, that the approximation error decreases should be fairly clear, because any smooth function can be approximated by a polynomial of sufficiently high degree. So that obviously decreases. Now, although it is implicit, we didn't really prove it, but you can find the VC dimension of this particular hypothesis class. And it turns out to be, I don't remember exactly, it's either m plus 1 or so, right? So which means that the sample complexity for this hypothesis class is roughly m. So if you increase m, the complexity of your hypothesis class increases, and therefore the sample complexity increases. So you need more samples, right? So for a fixed n, the estimation error now becomes larger as you increase m. So there's one thing, which is the number of samples you have. Because in the end, you have a data set of some fixed size. You can't increase the size of your data set depending on how much more complex you make the hypothesis class, right? So in that sense, typically when you want to design a learning algorithm, you have to assume that n is fixed. So for a fixed n, what is the best that you can do? And that is what I meant when I said that the estimation error increases. Any other questions? Okay. So before we begin, a couple of quick announcements. So firstly, Moodle is back up. So, but you'll have to re-register to Moodle if you've not done so already. The link for the Moodle course has changed. The updated link is available on my webpage. For those who have already registered for the course, you would have received an email asking you to re-register on Moodle. If you've not done so already, then please re-register. Right. And another announcement is a slight modification in the assessment. So we'll have 3 exams in the course, which will account to 20% for each exam. And programming assignments, those will be interspersed as we go through the course. The programming assignments may also have some theory or derivation component, but the majority of that will be programming. And that will also constitute 20% of the grade. And finally, there's going to be a project plus Viva. I'll give more details about this final thing in a few days' time, but this essentially will be a group project. I'll let you know what is the minimum maximum size of the group and what can constitute a project for this particular course. All right. But we also need to decide dates for the 3 exams because there are also a couple of external students. I would like to have this on a weekend. So tentative dates are 29th of August, 10th of October, and 14th of November. So that will be end of this month. Sometime in the first week of October and the end of the semester. All right. I'll also create a poll on Moodle to fix a particular slot. So we'll have the exam on either this date, or either the Saturday or the Sunday corresponding to these dates, and we'll need a 2-hour slot, roughly 2-hour slot for each exam. Right. This will mostly be a pen and paper exam, but more details will follow later. Right. So please join Moodle as soon as possible so that we can finalize these dates. Okay, and just a gentle reminder that in case any of you are planning to audit the course, then you must attend the exams or submit assignments and get a regular pass grade if you want an AU grade. Okay, so in the next couple of classes, we'll give a brief intro to optimization for machine learning, and we'll also explore what is different in deep learning. So recall that towards the end of the last class, we had a recipe for training a machine learning model. So we're given a hypothesis class H, which could be, say, all 2-layer neural networks with 100 hidden neurons. We're given a training set, a validation set, and a test set. So the first task is given, let's suppose that we have a classification problem with 0-1 loss. We typically choose a convex or at least some smooth surrogate loss function L prime, and you do regularized ERM on this surrogate loss function. Right. So you find a HS hat, which is obtained by minimizing this particular regularized empirical risk, where this empirical risk is with respect to the surrogate loss function. And if you have some hyperparameters to tune, maybe you want to change the number of hidden neurons in your 2-layer neural network, then you tune the hyperparameters using the validation set. Or if you don't want a separate validation set, then you do some k-fold cross validation. And at the end, you have, let's say, a neural network or a predictor, and you evaluate the performance of this predictor using the generalization error. Since we don't have the true distribution at hand, you estimate the generalization error using this empirical risk with respect to the true loss, and this empirical risk is taken with respect to the test set. Right? So that's the recipe that we want to follow. So we know what we should do given a learning problem, but really the what we want to focus on now is this particular problem. So how do we do this particular minimization? Is there is there a general efficient algorithm to perform a regularized empirical risk minimization? And what can happen? So for what kind of empirical risks and what kind of regularizers can we do different sort of things? So let's take a step back and try to abstract the problem. So let's assume that we have a parametric form for the hypothesis class. What do I mean by a parametric form? So every function in the hypothesis class or every predictor in the hypothesis class is some HW of X for W in R to the D. So let's assume that there are D trainable parameters. In the context of a 2-layer neural network, it could be all the weights and the biases. So I'm collecting all of the weights and the biases into one big vector of dimension D. And these are my trainable parameters. If I have a polynomial classifier, then it is a set of all the coefficients of the polynomial stacked together. All right. So if I have HM, my HW of X is indicator summation I equal to 0 to M Wi X to the I greater than or equal to 0 for this vector W in RD. So for many of the learning problems that we have at hand, you can represent it in this parametric form. Not all, but at least for the kind of problems that we are interested in. For instance, if you have a feed forward neural network, it can be represented in this parametric form. Okay. So given this parametric form for the hypothesis class, we want to solve this regularized ERM problem, which is you minimize this empirical risk using a computationally efficient algorithm. So now you want to minimize 1 over n summation I equal to 1 to n L prime of HW of XIYI plus G of W. Right. One thing to always keep in mind, because it's easy to lose in the notation, is that we want to minimize this with respect to the vector W. Right. So in particular, what does this function look like? This is basically a sum of n functions plus some other function. So it's a sum of n plus 1 functions, each of which depend on W in potentially some complicated way. Right. And even this, it could be the case that this G of W itself is a sum of multiple regularization terms, but I'm collecting all of them into one G. All right. So basically, we want to minimize a function of the form f of W, which is 1 over n summation I equal to 1 to n fi of W plus some G of W. That's the specific form that this optimization problem takes in the context of regularized empirical risk minimization. Right? And that's the problem that we want to solve. So given an optimization problem, we don't have any other information about this. So in general, what kind of loss functions do we want to consider? Let's see some common loss functions. One is the 0-1 loss, which we've already seen before. In the context of classification itself, there are multiple loss functions that one can think of, and these are surrogate loss functions. So you really want to minimize the 0-1 loss, but instead you perhaps replace it with the hinge loss, which you would have already seen if you've seen support vector machines. So in your machine learning course, if you go back to your notes, you'll have seen that the SVM is obtained by training or solving empirical risk minimization over this particular hinge loss. And this hinge loss is taken as a proxy for the 0-1 loss. There are other common loss functions which we'll encounter as we go along. One such loss is the logistic loss, which again, it's in terms of y prime. Okay, so one thing to just keep in mind is that I've made a small change in the notation. I'm assuming that my classification problem has label space -1, 1. And the reason I'm choosing -1, 1 is because I can represent all of these loss functions in terms of y times y prime. So if y and y prime are different, then y prime is -1. And an error occurs if y is not equal to y prime or y prime is less than 0. And that's really how you get these forms for the hinge loss and the logistic loss. Note that all of this changes if you change the label set. If I go from -1, 1 to 0, 1, then I'll also have to change the definitions of these loss functions. And then there's also the squared error loss, which you could use, but you generally don't use it in the context of classification. And absolute error loss. So if you sort of plot all of the loss functions, so this is the 0-1 loss, which is equal to 1 if y prime, this should have been y prime if y prime is less than 0, and it's equal to 0 if y prime is greater than 0. And you have the hinge loss, right, which is basically this particular line over here, the orange line. And the hinge loss essentially upper bounds the 0, 1 loss. So this means that if you achieve a certain hinge loss, let's say your generalization error with respect to the hinge loss is something, it's equal to 0.1, then you're guaranteed that the generalization error with respect to the 0, 1 loss is going to be less than 0.1, which can be very useful because if you train using the hinge loss and you can derive generalization bounds using the hinge loss, then that automatically translates to the bound on the generalization error with respect to the 0, 1 loss. And that's used in practice. All right. And the hinge loss has nicer properties because it is continuous and it is also convex, as we'll see. Right. And then you also have the logistic loss and the squared error loss and the Abs error loss. Okay, and what kind of regularization terms do we typically use? One is the L1 regularizer, as I mentioned in the previous class, and you usually do this to induce sparsity in your final train model. And so this, in a sense, corresponds to both model selection as well as regularization, because you're trying to put a bias on the model itself. You're trying to force sparsity in your model. Or you can also use the L2 regularizer, which, as I mentioned, has nice stabilization properties. So again, the goal now is to optimize this particular function. You want to minimize this with respect to W. So let's assume that we're given an arbitrary function f of W, and we want to minimize this function. One of the most commonly used algorithms for solving a generic minimization problem is gradient descent, assuming, of course, that the function is smooth. Essentially, it's differentiable. So you fix W0, an initial point, and then you keep moving along the direction of the negative gradient. So for capital T time steps, you basically start with W0 and set W1 to be equal to W0 minus some rho T times the gradient f of Wt. All right. And the reason why you take the negative of the gradient is, suppose you have a function that at least locally looks like this, and you are at an arbitrary point, say Wt. Right? The goal is to eventually reach this point of minimum, perhaps. So if you take the gradient in this case corresponds to the slope. The direction of the negative slope would essentially be this direction over here. So every time you keep moving along the direction where the function decreases. All right. So, and depending on how you choose this particular step size, the hope is that this eventually converges to this point of minimum. Right. So at every time step, what you do is you take Wt plus 1 to be equal to Wt minus some step size rho t times gradient of f of Wt. And you output, at the end of t time steps, you output what you obtain at the end. Sometimes, for the sake of analysis, instead of looking at W capital T, you look at this running average 1 over capital T summation T equal to 1 to capital T Wt. In certain kinds of proofs, it is sometimes helpful to look at this quantity rather than this particular quantity. Right? So this is a heads up. Yeah. Okay. I'm sorry. This is a typo. It should have been good catch. So it should be 0, 1, 2, 3 up to t minus 1. And even this should be, yeah, this is fine. Any questions? So hopefully you all seen gradient descent before. Now, the gradient descent is a basic algorithm. So given this, we have two free parameters to choose. One is the so-called learning rate or the step size sequence rho t. And there are a number of different ways of choosing this. Either you could set rho t to be some constant. Uh, in some learning problem, you also choose rho t to be sort of a hyperparameter, right? And you see what happens for different choices of the learning rate. And you can evaluate uh, the performance using the validation set. So one choice is to keep this constant, or you can have this to be some kind of a sequence that decays with t. So initially you have a large step size, and then you make the step size become smaller and smaller. And there's some intuition behind this, because initially you may be far away from the point of minimum, so you want to take larger steps. But as you get closer to the point of minimum, you want to take smaller steps so that you get closer and closer. If you take a large step size, then it can perhaps get in the vicinity of the minimum quicker, but then it will potentially keep oscillating and never get arbitrarily close to the minimum. And yeah, you don't know the shape of the actual curve. There can be a lot of things, and we look at that in more detail. Right now, it's what we're discussing is at a very high intuitive level, right? We'll also see what happens if the function is non-convex, and so on, because there could be local minima, local maxima, there could be saddle points, and we look at all of that later. But assuming that the function is sufficiently nice, essentially, if it is convex, then what can we do? You can choose rho t to be a constant or a decaying sequence, or you could also do line search. In a sense, you can reduce this problem. You try to optimize over rho t in every time step. And there are different ways you can do this. And one popular approach is this Armijo line search. And in many cases, this gives the best performance. And you can show that this is definitely going to be better than choosing it to be constant or according to a predetermined sequence. But if you want to keep your algorithm as simple as possible, which is typically what many people do when they train deep learning algorithms, you typically choose it to be either a constant or decaying according to some particular rule. So that's one thing. The other parameter that we need to choose is the number of steps, right? So for how many steps do you run gradient descent? And the reason why this capital T is so important is because it determines the computational complexity. Because every iteration of gradient descent incurs some computational complexity. The total computational complexity is basically T times the computational complexity of each step. So if T is large, then your computational complexity also grows proportionally. And that is also why choosing this learning rate carefully is important, right? Because if you don't choose it appropriately, then you may not converge to the point of minimum or local minimum, and that could increase the number of steps that you need to take, right? But a much more high level question is, does gradient descent at all converge to a local or a global minimum? And if it does, then how many steps do we need to find a point that is at least epsilon close to the either the global or the local minimum? So if you're given a function, or let's say a class of functions over which you want to optimize, how many steps of gradient descent do you need to take in order to ensure that the output of gradient descent is going to give you something that is epsilon close to the actual minimum, or at least the local minimum if the if you can't find a global optimizer. So in the next one or two classes, we'll try to answer this question, at least for a restricted class of functions. So again, remember that we want to get bounds on the number of time steps required for a general class of functions. There's no point in saying that, okay, if it's a quadratic function, then you need these many time steps. If it is log, then you need these many time steps. We want something that generalizes well enough. So the field of optimization is very vast and we can't cover everything. But here are some references for the specific topics that we'll cover in the next couple of classes. A very nice reference on convex optimization is this book by Boyd and Vandenberg. And we'll essentially cover topics from chapter 2 and chapter 3. So this will be basic definitions on convex sets and convex functions. I'm taking a lot of that material from this book. I will not cover everything in these sections, but it's very useful to just go through chapters 2 and 3 anyway. All right, and this also has a lot of worked examples and exercises, so it's a very nice reference. You can also go through lecture notes or the recorded video from my previous convex optimization course, especially because it covers parts on limits, continuity, gradient, Hessian, and so on in a slightly more rigorous fashion. But the analysis and variants of gradient descent and stochastic gradient descent, I'll take this from this book by Francis Bach. It's called Learning Theory from First Principles. Again, both these references are there on the course homepage, and a PDF is available for both these books from the authors' websites. All right. So a quick review. So for a given function, let's assume that f is a function from Rd to R. How do you define the gradient? It's basically the vector of partial derivatives of f with respect to each of the variables. So if I have f of w, right, where w is a vector, w1 up to wd, then this gradient is simply dou f by dou w1, dou f by dou w2, dou f by dou wd. And note that each of these is a function in itself. So when I say gradient f evaluated at w0, it means that you take the partial derivative of f with respect to w1, and this function is evaluated at the point vector w0. So for instance, if I have a function f of w is equal to w1, w2, what is the gradient? Correct. So the gradient would be, the first element would be the partial derivative of f with respect to w1, which is w2, and the partial derivative with respect to w2, which is w1. Right, and this is evaluated at w, so it's w2, w1. A useful property of the gradient, which you may or may not have seen before, is the following property, that if you take two vectors w and w0, then f of w0 plus epsilon times w minus w0. So you should think of this as the following. You take a point W0 and you move an epsilon amount, a small amount, in the direction of W. Right? The vector in the direction of W, starting from W0, is basically the vector W minus W0. Right? It is the slope, but exactly. But this is a high dimensional analog of this, and we want to get that concrete in our heads. Right? So it's W minus W0 is the direction along W. So if you take a small step along this particular direction, then this is equal to f of W0 plus the gradient of f of W0 transpose W minus W0 plus some quantity that decays faster than epsilon as epsilon goes to 0. All right. In fact, this is how you define the gradient in the first place, or the derivative in the first place. In one dimension, it is fairly clear because you always define the derivative to be, say, delta f divided by delta w, and you let delta w to go to 0. But in higher dimensions, you can't really use that definition anymore because both the numerator and because the numerator is a number, whereas the denominator, the difference between two w's, is a vector. So that earlier definition doesn't make sense. So this is essentially the definition of the derivative. Right? More generally, you can interpret this as an inner product between the gradient or the derivative and w minus w0. So in fact, this can be generalized even beyond functions on RD. For example, you could have functions on matrices or more complicated objects. All right. Likewise, if the function is twice differentiable, then you can also define the Hessian. How do you define the Hessian of? So this would be dou square f by dou w1 square, dou square f by partial w1, partial w2, and so on. Yeah. Okay. Yes. There should be an epsilon. That's correct. So this should be f of w0 plus epsilon times this inner product plus some function that decays faster than epsilon. Right? Okay. So the Hessian is basically, which I'll denote as del square f of w0, is now a matrix. And this is basically the derivative of the gradient. Right? And it's the d-dimensional analog of the second derivative. What can you say about the Hessian in general? So this is a symmetric matrix, right? And that just follows because dou square f by dou w1 dou w2 is equal to dou square f by dou w2 dou w1. Any questions? Okay. So far straightforward. We'll do much of the analysis of gradient descent and stochastic gradient descent initially for convex functions, and I'll say what happens if the functions are not convex. So to do that, let's have a few definitions. So a set is said to be convex if essentially for every w1, w2 in the set, the straight line joining these 2 points, so the line segment joining these 2 points, W1 and W2, also lies within the set. So if I have a set like this and I take 2 points, say W1 and W2, then any point along the line joining W1 and W2 can be expressed as lambda times W1 plus 1 minus lambda times W2. And this, if any point on this line lies outside the set, then the set is not convex. All right. And such a combination, lambda times W1 plus 1 minus lambda times W2, for lambda being strictly between 0 and 1, is called a convex combination. Right, so it's a special case of a linear combination of two vectors. We'll also say that the function is strictly convex if this inequality is a strict inequality for all W1 not equal to W2 and lambda not equal to 0 or 1. All right. And we'll say that the function is concave if minus f is convex. Right. Or in other words, the inequality flips the other way around. So the function the function is convex if basically f of lambda w1 plus 1 minus lambda w2 is less than or equal to lambda times f of x1 plus 1 minus lambda times f of x2. So if I take a function f, I take 2 points. Let's call this w1 and w2. Then, as we've seen before, lambda w1 plus 1 minus lambda w2 is essentially the straight line joining w1 and w2, right? So if you fix a particular lambda, so this is my w, which is equal to lambda w1 plus 1 minus lambda w2, then this point would essentially be f of w, which is f of lambda w1 plus 1 minus lambda w2. And lambda f of w1 plus 1 minus lambda f of w2 would essentially be some point along this line joining f of w1 and f of w2. So this basically says that if you take any 2 points along this curve, then the straight line joining these 2 points always lies above the curve. Right? So that's essentially the definition of a convex function. You take any 2 points along the surface that defines the function, then this straight line joining these 2 points will lie above the function itself. And it is strictly convex if the straight line lies strictly above the function surface itself. More in the context of gradient descent, it is more useful to look at this first order condition of convexity. I guess in your high school, you would have seen the second order condition for convexity, which is that a function which is twice differentiable is convex if and only if the second derivative is greater than or equal to 0. Right? That would have been, in fact, sometimes that's introduced as a definition for convex functions. But this particular form is more general because it applies to even functions which are not differentiable. So a function is convex if and only if the following happens: f of w is greater than or equal to f of w prime plus the gradient of f of w prime transpose times the w minus w prime. So let's look at the quantity on the right hand side. If you fix a particular w prime and you view this right hand side as a function of w, right? Let's call the right hand side to be some g of w. Then what kind of a function is g of w? Okay, it's affine, right? And what does it look like in n dimensions? What kind of a set? It's basically a hyperplane in d dimensions, right? So this right hand side is basically a hyperplane. And because it passes through this w prime, it in fact it has another property. Can you even in one dimension, what does the right hand side correspond to? Is it a general hyperplane or a general line, or does it satisfy some additional property with respect to the function itself? So let's view the right hand side as a function in one variable, right? So it's basically f of w prime plus the derivative of f at w prime times w minus w prime. What line does that correspond to? What is the slope of the line? It's f dash of w. So it, of course, if as you can see, it basically passes through w prime comma f of w prime, but it has another nicer property because of the slope. So is it some line that passes through through w prime, or is it something else? Yeah, it's basically the tangent line, right? Or in d dimensions, it's the basically tangent hyperplane that passes through at w prime. So it's the tangent plane or tangent hyperplane at the point w prime. So if you have this function that looks something like this, and you take this particular point w prime, then the right hand side essentially corresponds to the tangent at this particular point. And what this lemma is saying is that the function is convex if and only if the tangent always lies at, you take any point and you draw the tangent line to the function, the tangent always lies below the function itself. All right, so you take this point and draw the tangent, it lies below the function. You take the tangent at this point, it lies below the function. So no matter which point you take, the tangent line always lies below the function. It's only then that the function is convex. Right? So this is a different view of convexity compared to the so-called zeroth order condition, which is that you take any 2 points, the straight line joining these 2 points lies above the function. And one geometric or intuitive way to think about it is the following. You take what does a convex function look like? So it's something like a bowl, right? So if you take, say, a plane below the bowl, if you take it to touch the bowl at any point, that plane is always going to be below the bowl itself. And you take any 2 points on the bowl and you join these 2 points, it's going to lie above the bowl. Right? So these are two different geometric views of any convex function. Let's say that this doesn't happen, right? For example, if the function is non-convex, then there will be some point where this tangent lies above the function itself. All right. Okay. Any questions? Great. Now, what happens if the function is not differentiable? So this first order condition for convexity assume that the function was differentiable. But as we'll go along in this course, we'll see that a lot of the functions that we're actually interested in, including some of the nice loss functions or activation functions that we want to look at, they're all non-differentiable. Even if you go back to one of the examples that we saw earlier, the hinge loss, right, which we wanted to use as a surrogate loss function, this is not differentiable. It's not differentiable at this point 1, right? So in this case, it turns out that the function is convex. Then a similar idea that we had just now also extends to functions that are not differentiable. So let's look at a function that looks something like this, right? Now, if I look, let's assume that this is point 0. So if we look at any w that is greater than 0, the derivative is equal to 0. The derivative is well defined and it's equal to 0. And for w less than 0, maybe the derivative is minus 1. At this point 0, I can't really define a derivative. But then if I look at so-called tangent line, so the question is it possible to construct a line that is passing through any one of these points which lies strictly below the curve itself, the function itself? If you take any point which is greater than 0, so this is 0. If you take any point here, then yes, you could construct a line that passes through this particular point so that the function is above this particular. Similarly, if you take any point less than 0, then again I can construct a line such that the function is always is never below the line. What about the point 0? Is it possible to construct a line which passes through this particular point and still lower bounds the function? I am looking at this particular example. In this case, yes. In fact, it's not just one line. I can construct infinitely many lines. Right? For example, this particular line passes through this point and lower bounds the function. Right? And we'll use this exact idea to define the so-called subgradient of f. So we say that a vector which is indexed by W0. Let's look at a point W0 in the domain of F. We'll say that VW0 is a subgradient for F at W0 if the tangent plane, if it's possible to construct a tangent plane passing through W0 F of W0 and still lower bounds the entire function. All right. In this case, this or the slope of this particular orange line corresponds to the subgradient. One thing to note is that the subgradient may not be unique. By that, I mean that I could potentially find two different vectors v such that f of w is greater than or equal to f of w0 plus v transpose w minus w0. In other words, I could find more than one tangent hyperplane at which lower bounds the function at this particular point. So if there are more, in general, the number of subgradients at a point W0 could be more than one. So the set of all possible subgradients at that point W0 for the function f is called the subdifferential set. And I'll denote this as this partial f of W0. Right. So just keep in mind this notation where this will define a set. Okay. So a function f is convex if and only if it has a subgradient at every point. That is, you can find at every point, you can find a tangent hyperplane that lower bounds the entire function. Or equivalently, you can find an affine function that passes through, for which the corresponding hyperplane passes through that particular point, and it lies below the function itself. And this particular first order requirement doesn't even require the function to be differentiable. Right? So one thing that is very important for us is that in the definition of the subgradient is that now when we want to do gradient descent, we could in principle just do subgradient descent. So let's say that the function that we want to optimize or we want to minimize is not differentiable at all points, but it is convex. Then what we can potentially do is at the point, if we at some point we reach a point where the function is not differentiable, instead of using the gradient at that particular point, we could use the subgradient because the function is convex. Right, and then proceed. And in fact, this is what is actually done in practice. Because let's say you want to minimize the hinge loss, or as we'll see, as we'll explore some activation functions later on, we'll have activation functions which are not differentiable. The ReLU, for example, is not differentiable. Right? So then you can't use a variant of simple gradient descent because it's not differentiable. You instead replace that with the subgradient. Any questions? All right. Now, here's a more familiar second order condition for convexity that you would have seen, which is that if f is twice differentiable, then the function f is convex if and only if the Hessian is positive semi-definite at all points. And it is strictly convex if it is positive definite everywhere. How do you define positive semi-definiteness? Yep, there are again equivalent definitions. So one is that X transpose AX is greater than or equal to 0 for all vectors X. It's positive definite if this is strictly greater than 0 for all non-zero vectors X. Or another way of saying, what can you say about the eigenvalues of A? All of the eigenvalues are non-negative. It's positive definite if all of the eigenvalues are strictly greater than 0. So what if the matrix A has complex eigenvalues? Can that happen? If I give you an arbitrary matrix A, right, it could have purely real or it could also have complex eigenvalues, right? Yep, correct. So we're implicitly assuming that A is symmetric. Every symmetric matrix has only real eigenvalues. Okay, good. Any questions? Great. So here are a bunch of exercises for you. We'll not go over all of these, but for each of these functions, I want you to compute whether the function f is convex or concave or neither convex nor concave. So one set of examples is all of the loss functions that we had earlier, right? Which included the 0, 1 loss, the hinge loss, the logistic loss, the squared error loss, and the abs error loss. Where you take the variable to essentially be just y prime. All right. So the first is indicator y less than 0. The second is f of y, which is minus, I think, 1 minus y if y is less than 1 and 0 if y is greater than or equal to 1. And I think I had, let's say, f of y equal to y square. And f of y equal to mod 1. So out of these, which are convex and which are non-convex? What about the first one? Is that convex? It's not convex. How do you prove that it is not convex? I want you to give an analytical proof to show that the function is not convex. Again, you can use either of these three properties that we had. We had three equivalent ways of defining convexity. Okay. Can you give a specific example and show that? Okay. If you draw the tangent at any point, okay. Again, that's you're giving me a visual proof, right? I want you to give me an analytical proof. Okay, so can you say that any discontinuous function is not convex? Okay, in that case, I'd like you to prove that. In fact, that's a good exercise. I think that is already there as an exercise. Yes. So if f is discontinuous, then it's neither convex nor concave. Right? So one way again is to take a specific pair of points. One pair of points that you can take is maybe -1, 1, and the point, I don't know, 0, 0. Right? So all you need to show is that the property 1 is violated. That is, you can find a lambda between 0 and 1 for which the first definition doesn't hold. What about the second one? Okay, how do you prove that it is convex? Okay. Okay. Okay, so one way is maybe to go through a case-by-case analysis. You take two points. You take the 2 points to the right of 1, 2 points to the left of 1. Both of them are fine. Then you take a point to the left of 1 and to the right of 1. Right? Okay, what about the third? How do you show that this is convex? In this case, it's twice differentiable, so you can just use the second derivative property. And second derivative is equal to 2, which is greater than 0, so it's in fact strictly convex. What about the third? Yeah, you could use the subgradient at 0, or what you could potentially do is there's something more general that you can potentially use, which is triangle inequality. You take any norm, f of x equal to norm of x, and this could be any norm. In particular, the absolute value is the L1 norm. So the any norm satisfies the triangle inequality. So f of lambda x plus 1 minus lambda x prime is norm of lambda x plus 1 minus lambda x prime, which by triangle inequality is less than or equal to lambda times or norm of lambda x plus norm of 1 minus lambda x prime. Which is equal to, again by the property of the norm, lambda or mod lambda times x, which is lambda times norm of x plus 1 minus lambda times norm of x prime, which is just lambda times f of x plus 1 minus lambda times f of x prime. All right. So one thing that you have to be very careful about, and many students make the mistake, is just trying to use the second derivative test. It's differentiable for this particular example, f of y equal to mod y. What is the derivative of f of y at any point not equal to 0? It's equal to, fine, it's mod y by y. But y not equal to 0, right? So then it's either +1 or -1. And they say, okay, fine. On what is the second derivative? It's equal to 0 on both sides, right? Fine. So the second derivative is greater than or equal to 0, therefore it is convex. But that doesn't hold in this case, right? Because it's not differentiable at one point 0, and that itself can change the convexity or concavity properties. Because I can always construct functions, for example, minus mod y, that also has second derivative equal to 0 at all points except 0. But the second case, minus mod y is concave, mod y is convex, right? And I can very easily construct examples where the second derivative is equal to 0 at all, but maybe 2 points where it is not defined, and the function is neither convex nor concave. Right? In this case, the second derivative is equal to 0 at all points except these 2 points where it doesn't exist. But this function is neither convex nor concave. Okay. Here are a bunch of other examples, and I encourage you to solve each of these. You can expect some of these to even appear in the exam. All right. And you can also prove a bunch of interesting properties for convex functions. So for example, if you have f1, f2 up to fd, which are all convex functions on R, and you apply these component-wise to a particular function, to a vector x, then this function is also convex. Again, it just follows by as a straightforward definition. Right? And it's easy to verify. And this is important for us because let's suppose that we have a feed-forward neural network and we choose a convex activation function. Then if the activation function which is defined on R is convex, then this extension to vectors is also convex. And that's a useful property that we can use. All right. And similarly, if you have convex functions, then any convex combination of these convex functions is also a convex function. In fact, any non-negative linear combination of convex functions also gives you a convex function. And if you compose a convex function, if you compose an affine function with a convex function, then the resulting function is also convex. And this is exactly the setting of our feed-forward neural network, right? So if f, your activation function, is convex, then f of aw plus b is also convex, right? But then you have to be careful about just composing convex functions. You cannot, in general, conclude that if f1 and f2 are convex, then f1 of f2 of w is also convex. That doesn't always hold. But then you can say something more. If one of them is non-decreasing or non-increasing, then you can say that the composition is also convex. And I want you to derive that exact relationship. So under what conditions on f1 and f2 is this composition also guaranteed to be convex? Assuming that, of course, f1 and f2 are both convex. But nothing else. You have no other information about f1 and f2 except that both of them are convex. And maybe one of them is non-decreasing or non-increasing. Which of these can you use to say that f1 of f2 is also convex? All right. And as I said, if f is discontinuous, then it is neither convex nor concave. Right. So that's something that we have to keep in mind. Whenever we're choosing either a loss function or an activation function, we don't want it to be discontinuous. It's okay if it is not smooth, but discontinuity is something that we want to desperately avoid. And if f is convex, then W star is a minimum of f if and only if 0 lies in the subdifferential set, or 0 is a subgradient at that particular point. All right. Again, I say W star is a minimum, which means that there could be multiple minima. Can that happen for a convex function? Can a convex function have more than one minimum or one minimum point? Yep, yeah, as you said, it could be flat, right? A function that looks, say, like this, right? This is a convex function, and there are infinitely many points which are points of minimum. The minimum value is unique, right? But the point of minimum is not unique, right? So here are some activation functions that we'll commonly encounter. Again, for each of these activation functions, I'd like you to find whether these activation functions are convex or concave or neither convex nor concave. So one is the ReLU function. The other is the logistic sigmoid, tan h. There's also a variant of the tan h. Again, if you plot these functions, then it's very easy for you to determine or guess whether it is convex or concave. But again, I want you to prove this purely using analytical methods. You can use one of those three different properties, either the zeroth order property or the first order property or the second order property. All right. So the tan h looks something like this. It's a smooth twice differentiable function, whereas the hard tan h essentially looks something like this. Right. Again, this hard tan h is not differentiable at all points. As you can see, it is not convex. And again, there are a bunch of other activation functions that I'd like you to look at. We will revisit all of these later on when we look at feed-forward neural networks in more detail. But basically, what I'm trying to do is also introduce you to some of the terminology and some of the ideas that we'll encounter later on at this point and try to connect it to the theory that we're trying to develop. Another useful property of convex functions is Jensen's inequality, which says that if f is a function which is convex and x is any random vector, then f of expectation of x is less than or equal to expectation of f of x. Now, for example, if x is a vector that takes one of two different values, let's say x1 with probability p and x2 with probability 1 minus p, then this essentially just boils down to the definition of convexity, right? Because what is expectation of x? P into x1 plus 1 minus p into x2, right? Which is just a convex combination, which is less than or equal to p times f of x1 plus 1 minus p times f of x2. So this is just the definition of convexity. Again, for random variables which have a finite support or even countable, then this is very easy. But it becomes a slightly more non-trivial when x is a continuous random variable, because then what you have is f of integral the density of x is less than or equal to integral p of x f of x dx. All right, so I'm using px just for the density. All right. Any questions? Just for the sake of proving certain results, we'll impose further restrictions on the functions that we want to analyze. So we'd say that a function is a differentiable function f is mu strongly convex if the following happens. So earlier we saw that a function is convex if f of w can be lower bounded by the corresponding tangent hyperplane at that particular point. It is strongly convex if it can be lower bounded by not just the tangent hyperplane but also a quadratic function. Right? So there is some quadratic function that passes through the point w0 and lower bounds the entire function. So effectively, the function is lower bounded by a quadratic at every point. So a function that looks like this. Let's say I take this particular point. This is the tangent hyperplane. What this says is that there is some quadratic function that lower bounds the entire function. So in particular, it rules out cases where the function is flat over an interval. Right? If you think about it, if the function is equal, let's say equal to 0 over some particular interval, then this function is not strongly convex. And strong convexity, there are a number of equivalent properties of strong convexity. One is you can just show that the function is mu strongly convex if g of w, which is f of w minus mu by 2 times norm w2 square, is convex. But a more useful property of strongly convex functions is that if f is mu strongly convex for some mu greater than 0, then it has a unique minimizer. So the point of minimum is unique. And that is something that will be very useful for us. How do you prove this? Again, fairly straightforward. So let's try to prove the second property, which is that f is mu strongly convex implies that f has a unique minimizer. So by the definition of mu strongly convex, if you take any point f of w, this is greater than or equal to f of w prime. Let's take the second point over which we are expanding the right hand side to be w star, any minimizer. So let w star be a minimizer for f. At this point, we don't know whether the function is a unique minimizer or not. There could be other minimizers, but let's say I pick a W star that is one such minimizer. So f of W is greater than or equal to f of W star plus gradient f of W star transpose W minus W star plus mu by 2 norm W minus W star square. Now this is just by definition of mu strongly convex function. Yeah. I'm sorry? Huh? They're basically the same. So when you say strongly convex, it essentially means that it is strongly convex with some parameter mu. Because remember, it is strongly convex if this is lower bounded by a quadratic, by which quadratic that determines the mu. So strictly speaking, I should say mu strongly convex all the time. Sometimes I just say strongly convex, assuming that implicitly there is one such mu greater than 0. Not necessarily. So again, there are links to the Hessian, but at this point, we just use this as a property. Again, keep in mind that for a function to be mu strongly convex, it does not have to be twice differentiable. Right? The Hessian may not even exist at all points. But I can still have this mu strongly convex definition. The gradient has to exist, but that's all I require at this point. Right? Any other questions? Okay. So again, I get this just by definition of mu strongly convex. But what can I say about the second term? What should this be equal to? 0. Why? It's a point of, it's a minimizer. So W star is a minimizer. So the gradient at that particular point should be equal to 0. So the second term is equal to 0, right? So f of W is greater than or equal to f of W star plus mu by 2 norm W minus W star squared. If W is not equal to W star, then what can I say about the second term? If W is not equal to W star, it is strictly greater than 0, right? So this says that if you take any other point other than W star, then f of W is strictly greater than f of W star, which means that W star is the unique minimizer. There's no other minimizer possible. Right? If this were not mu strongly convex, then I don't have this term over here, and therefore I can only say that f of W is greater than or equal to f of W star, which is also how you prove that if a partial derivative is equal to 0, then it's a point of minimizing. Right? Because if the gradient is equal to 0 for a convex function, then f of W is greater than or equal to f of W star. Right? Now this inequality over here gives us a little more information than just f has a unique minimizer. It also tells you that the farther away you go from the minimizer, the function value can only be larger. So if you're really far away from the minimizer, then the value of the function is going to be much, much larger. Right? And again, this is purely in terms of the Euclidean distance. Okay. So in the next couple of classes, we'll explore some more properties of these strongly convex functions and see how gradient descent behaves on strongly convex functions and see what happens if the function is not strongly convex. Okay. So let's stop here.